Okay, thank you very much. I'm Hiroki Takasue from NTT BIL. And actually, NTT Basic Research Laboratory is not a part of NTT Research Institute, but it is one of the NTT laboratories that directly belong to the NTT Corporation in Japan. So in this presentation, I'd like to update current status of our optical machine being developed in Japan. Okay, so this is the animation of the coherent ID machine that is made by NTT headquarters. I skipped explaining the function, how coherent ID machine works, because we had a lot in this summit. So in short, we are using the DOPO pulses as a to represent the eigenspins. And by coupling those DOPOs by using measurement and feedback, we can simulate the Eisen model on a networked optical oscillators. So in 2016, NTT, in collaboration with many institutions such as NII, Osaka University, Tokyo University, and the Sango University, constructed large-scale coherent eigenspin. And under the Japanese funding project called IMPACT, in which Professor Yoshi Yamamoto played the role of the project manager. So we developed the key technology of our large-scale machine is the generation of the thousands of time multiplexer DOPO pulses using the huge kilometer-scale pipe cavity. And those DOPO pulses are flexibly coupled via the measurement feedback. So all coupling among the 2000 spin can be possible with this scheme. And with this setup, we experimentally confirmed that our CIM finds a solution to the 2000 node max cut problems. And we showed there was some computational advantage over simulated annealing on CPU. So in this talk, I'd like to briefly talk about our recent experiment as the basic research of the CIM. And also, I'd like to talk about our effort to realize a computation system based on the concept of the coherent. So let me begin with the first one, which is the implementation of the external field term. So in general, the Hamiltonian of the Eisen model is given with this equation. Yeah, given as this equation, where the first term in the right-hand side corresponds to the spin-spin interaction term, and the second term is the external magnetic field. And however, in the previous version of the CIM, this magnetic field term has not been implemented. But this term is very important term for mapping various combinatorial optimization programs to the Eisen model. So in the current updated version of the CIM, we implemented this term by simply modifying the FPGA logic so that the feedback signal includes this term, which is proportional to the magnetic field vector term that is for the given Eisen model program. So in order to confirm this magnetic field term correctly works, we did a very simple experiment, which is to simulate the 2D anti-ferromagnetically coupled 2D square lattice with and without external magnetic field. So this is the experimentally obtained the temporal evolution of the 2D square lattice without and with magnetic field as a function of the number of circulations in the cavity. So at the without when there's no magnetic field, which is just a conventional coherent machine, at the circulation number of 0, we obtain the spin configuration is totally random and very broad pattern is obtained. But as the circulation goes on, that we begin to see the formation of the anti-ferromagnetic lattice and And at first we see some domain walls, but those domain walls goes away. And finally, around 800 circulation, we obtain the ground state. So in this case, at this final state, the magnetization becomes 0 and the spin-spin correlation became -1. However, with a strong magnetic field term, the station completely changes. The starting point is almost the same, very random phase pattern, but those spins are forced to align into the same direction. So finally, what we obtained is that magnetization is almost 1, and the spin-spin correlation is almost 1. So we did the same experiment with different magnetic field amplitude, and plotted the spin-spin correlation and the magnetization as a function of the magnetic field amplitude. So for both 1D and 2D anti-ferromagnetically coupled isomers. So as you can see, we obtained a clear crossover, clear transition from the anti-ferromagnetic state, which is governed by the spin-spin interaction, to the ferromagnetic state forced by the external field. And more importantly, those curves fits very well with the theoretical curve obtained with the analytical solution in the case of 1D and the MC result in the case of 2D. So now we can simulate the Eisen space in the external field with our options. Okay, the second topic is to simulate 2D Eisen model on CIM. So the purpose of this experiment is to confirm whether our CIM can emulate the interesting phenomena such as phase transition using our optical setup. So we put the most well-known, one of the most well-known Eisen model, which is the two-dimensional square lattice Eisen model onto the CIM, which is shown with this picture. So those spins are aligned in a 2D square lattice, and the nearest neighbor spins are coupled with coupling coefficient J. And we can thanks to the measurement filter, we can put the periodical boundary condition very easily by using the measurement filter. So which was assumed in most theoretical most cells. So then what we expect is the magnetization as a function of the beta J behave like this with these blue lines. So according to the exact solution of the two-dimensional Eisen. So this theory says is at the beta J equal to about 0.44 point, we should observe the sharp lines of the magnetization. So in order to obtain, so our purpose is to obtain this curve experiment. So we need to change this beta J. So in order to change beta J, what we did is we changed the coupling between the OPOs. More exactly, we changed the amplitude of the measurement feedback signal, and then we assume the energy distribution obtained by the CIM is in canonical distribution. So with this assumption, effective beta J can be obtained by fitting experimentally obtained average energy, which corresponds to the internal energy of the Eisen model, and by fitting this average energy to the theoretical internal energy curve, which was obtained by assuming the canonical distribution. So like this, the experimental data is fitted to this U beta J curve so that we can obtain some hypothetical effective temperature beta J. And using this estimated beta J value, we can plot several physical parameters by using the experimentally obtained energy distribution. So for example, when we plot the entropy as a function of the obtained beta J, it fits very well with the theory. So this implies that our assumption of canonical distribution is more or less valid. And I forgot to mention that in this experiment, DOPOs are oscillated well above threshold. And then we plotted the magnetization as a function of beta J by using the experimental data. So our experimental data is shown by this blue dot, whose behavior is very similar to the analytical exact solution for the n equal to 100 graph. So I also forgot to mention that our experiment was done with the number of nodes of 100. Although there's a slight difference from the analytical curve. However, we consider that the phase transition-like behavior, which is close to analytical solution, is so this shows CIM may simulate the behavior of the iodine spin at the final temperature. Okay, so then let me move on to the third topic of our basic research, which is to simulate spiking neurons by using the DLPOs. And the concept of emulating the behavior of the spiking neuron by DLPO is actually conceived by this guy, Kensuke Inaba of our group, who is the theorist of the atom optics. And his concept is very beautifully expressed in an experiment by Takasue. And we had lots of good discussion about this topic. Actually, we learned a lot about those neurons and neural network from IHAR group of the Tokyo University. And we especially thank previous speaker, Kim-san, for the very good discussion on this topic. So signal processing with spiking neuron is now an important topic. The ultimate purpose may be to understand the function of how human brains function, and also it may lead to the development of the next generation artificial intelligence. And it is well known that there are two major classes of spiking modes that is classified by Hodgkin. So class one is something like this. So in neurons, when neuron gets some stimulation or input signal and that exceeds some threshold value, the neurons start to generate a signal, spike signal. And in the case of class one neurons, when the input strength exceeds the threshold, the neuron start to spike at a very low frequency. And as we increase the input strength, the spike frequency continuously changes. So that is the class 1 neuron. On the other hand, in the case of class 2 neurons, when input strength exceeds some threshold value, it starts to oscillate at a relatively high frequency. And the frequency doesn't change so much as we increase input strength. So class 2 neurons show the sudden and discontinuous change of the spike frequency. So by using our DOPO neurons, we can express both classes. So that is the most interesting point of neurons. So the concept of the artificial spiking neuron with a pair of DOPO is summarized here. We use two DOPO pulses, which is denoted by V pulse and W pulse in this picture. And those are coupled via measurement feedback by using opposite sign optical coupling. So, for example, when feedback from V to W pulse is given by JWV, the feedback to W to V pulse has the same amplitude, but has a different sign, opposite sign. So, by using this opposite sign connection, we observe the energy transfer, periodical energy transfer between two OPOs is observed. And that can be used to emulate the behavior of the spiking neuron. And this behavior of the spiking neuron can be maybe simply understood by using the simple equation shown here, which is based on the CSV equation developed for the DOPO system. So these equations are very similar to that of the coherent machines one. But the important difference is between the V and W pulses, we have two coupling terms that has opposite sign. And also to simulate the external input signal, we put the external bias amplitude to one of the DOP pulses. And in our experiment, we first set this external bias amplitude to the large negative value. And then we gradually increase those external bias amplitudes so that we can increase the stimulation to the neurons. So this is one of the example of the experimental result in which as the time goes, the external bias amplitude was increased from large negative value to zero. So what we observed is at the temporal position of about 2 milliseconds, the system exceeded some threshold. So it began to oscillate, but first at a very slow frequency. But as the external bias amplitude increases, the pitch between those pulses becomes narrower and narrower. So class 1 type behavior is observed in this experiment. And actually, this type of class 1 neuron was obtained when we pump DOPO strongly. So actually, the previous result was obtained when the normalized pump amplitude, where P equal to 1 corresponds to the oscillation threshold, was and the when P was set at the larger than 1, we observed class 1 type of behavior. On the other hand, when we use a relatively small pump, for example, when we use P equal to 0.6, we observe this kind of behavior. In this experiment too, we changed the external bias from negative value to zero value and large positive value. And in this experiment, when the system exceeded the threshold at around 4 milliseconds, but from the beginning, the frequency, oscillation frequency, is almost same, and it doesn't change throughout while we increase external bias. So anyway, the point is that by simply changing the pump power to the DOPs, we can realize both class 1 and class 2 neurons. And yeah, so since there's no time, I skip the detailed explanation, but we try to use this spiking units. So this is application, one example of application, which is to do complete vectorial optimization by using spiking neurons as our artificial screens. So now 2 pair of the DOPO pulses, that's from the spiking neuron, plays role of the eigen speeds, and we put the network to the spiking neurons, and we try to solve the 150 node dense graph problem. It's this spiking neurons. This is the experimental result obtained with the spiking neural network as well as coherent agency, conventional coherent agency. So the notable difference is the probability of obtaining a ground state was about 10 times larger with the spiking neuron. This is probably due to that in the case of spiking neurons, by coupling the spiking neuron, the effective pump amplitude changes adaptively. So a particular node that has higher energy has a higher spiking frequency, so it rotates the phase so rapidly to find the lower energy state. So that kind of automatically adaptive behavior is obtained in the spiking neuron, and that leads to the better solution success probability in solving combinatorial optimization. That is our current hypothesis. But of course, this is one experiment using one particular instance, and we need to more more thorough investigation is very needed. So with the last 5 minutes, I'd like to talk about our effort to realize a computational system called LASOL. LASOL means laser sorter. So LASOL is currently NTT is considering making a computation system, real computation system based on the concept of the coherent algorithm, which we call LASOL. And actually, our first generation machine, which was actually constructed by only 2 persons, Takahiro and me, it was something like this. And this is just a bunch of optical components placed on an optical table. And most of the parameters and the equipments are manually controlled. And in the following few years, we put those optical components into the 19-inch line and put the temperature control to the 4 optics and packed those setup into the very nice box and we started calling it LASOL. However, this is inside the box is very beautiful, but the inside is actually the same as those optical experimenter setup. So in order to make a serious computation system, we need to do a lot of things, such as more stabilization is of course needed, and the scaling up is important, and the compactness, reliability is very important for the computation system, and the management system, software stack, application, that kind of thing, all should be considered. So in order to tackle those problems, for NTT, in NTT laboratory, we formed the CI and LASOL team that is listed here. So the basic research laboratory where I belong to is mainly doing the fundamental research on coherent algorithms, but some people, including myself and Onjo-san, is working on the hardware, development of the hardware. And the Kensuke is a great force to find application of this. And the LASOL hardware is now mainly developed by the Device Technology Laboratory and the Network Innovation Laboratory of NTT. And the software stack for CIM computation and as well as application are now pursued by Computer and Data Science Laboratory. And in the October 2020 project called LASOL Promotion Project, LPP, was formed to accelerate the development of the LASOL hardware. And the people that are surrounded by those green lines are the members of the LPP. And Ryoichi Kasahara is the project manager of LPP. And those NTT people are now collaborating with several NTT group companies and try to form some cooperation with external companies, so that so now we are trying to build an ecosystem to pursue the development of the LASOL. So, and at the Computer and the Data Science Laboratory are actively pursuing developing the software stack for computing with LASOL. So they developed the Python-based software development kit for LASOL, and they also developed a system that enables remote access to LASOL. And the search for application is also going on among the Computer and Data Science Laboratory and VRL, together with external partners. So our target, we are now searching for the key application, and the candidates of such application are shown here. And finally, we expect that LASOL will play an important role as one of the next generation computers for the IoT concept that is pursued by whole NTT group. Okay, so this will end my talk. Thank you very much.